Okay, so the next case we want to have a look at is this one here, where C is this category that has three objects and it has this arrow alpha from 0 to 1 and beta from 1 to 2. Of course, the category will also have to have identity arrows and this arrow beta after alpha, but that's it. This is the so-called walking category on three objects. So in this case, if C is this, what is set to the power of C? Well, it's this category of bouquets with two layers of petals. So a typical kind of object of this category is sort of what's pictured here. We see A, B, and C are getting sent to sets, and this sigma and mu here. Well, I was calling them alpha and beta up there. Let me call them sigma and mu. Yeah. These kind of arrow, sigma and mu, obviously they get sent to functions under this functor x from C to set. So basically an object of sets to the power of C in this case can be considered to be these kind of three sets, x of a, x of b, and x of c, where there's a function from x of a to x of b and a function from x of b to x of c. But a nice way to visualize these kind of things is basically as a kind of bouquet where we have two different sort of layers of petals. So we think of the elements of x of c as vertices. We think of sort of the elements of x of b as petals of the first level. And, you know, there's vertices can have different sort of sets of petals, depending on what gets sent to a sort of petal under x of mu. And then for each sort of petal, for example, petal little b here, there can be different sort of petals on the second level that get sent to them, and that's what happens under this function x of sigma. So x of sigma sends 2 and 3 to b, so these second order petals 2 and 3 are petals coming off this petal little b, which is a petal of the vertex alpha. Okay, so this is this idea of this kind of category of bouquets with two layers of petals. Here's another example. What happens when C is this category here? So in this case, we have objects E, V1 and V2, and we have an arrow S from E to V1 and an arrow T from E to V2. Well, in this case, when C is this kind of category, set to the power of C is the category of bipartite graphs. And so a typical kind of object in this type of category is a functor from C to set like this. So it'll be associating V1, E, and V2 with these different sets. And then this arrow S obviously becomes a function x of S. This arrow T becomes function x of T. And this all defined for us a sort of bipartite graph, because what we're really saying here is that we have some set of edges, but for a sort of member of this set of edges, its kind of source vertex is always going to be in this kind of left-hand set, V1, well, x of V1, whereas its target vertex is always going to be in this kind of right-hand set, x of V2. And so every edge is going to be going from x of V1 to x of V2. And therefore, we're going to have a sort of bipartite graph. So we can picture the sort of objects in this category set to the power of C, in this case like this. Okay, so here's another example. This is the sort of dual to the category previously mentioned. So let's consider this case here now, where C is this category with objects A, B, and C, and then there's an arrow sigma from A to C and an arrow mu from B to C. And so in this case, set to the power of C is going to be this category of bouquets with two kinds of petals. All right, so basically an object in this kind of category, we can think of it as a functor from C to set. It's going to be associating with these different objects A, B, and C with sets. And then sigma. So we can think of x of C here as this kind of set of vertices. And then we can think, well, we've got this kind of one set of petals x of A, and another set of petals x of B, and then x of sigma and x of mu are telling us which vertices those sort of type 1 petals or red petals, and which vertices those blue petals are coming off. Sorry, which petal, and then x of mu is telling us which vertices those red petals have, and then x of sigma is telling us which vertices those red petals have, whereas x of mu is telling us which vertices those green petals have. So this kind of object here, this functor from C to set, is visualized like this in this category of bouquets with two kinds of petals. So, I mean, notice x of C here, that's our set of vertices. X of A, that's our set of red petals. X of B, that's our set of green petals. X of sigma, that tells us how, that tells us which vertices these red petals have. And x of mu, that tells us which vertices these green petals have. Okay, so onwards then. Here's another one of these kind of cases. So what about if C is this category here, which has three objects? So it has objects V, L, and E, and then there's arrows S and T from E to L, and also an arrow D from L to V. Well, there's a couple of ways we can think of set to the power of C in this case. We could think of it as a category of vertex labeled graphs, or a category of graphs with vertices as loops. So I'll explain this in a moment. But as usual, we can sort of just think about, well, in set to the power of C, the objects are going to be functors from C to set. So what does such a thing look like? Well, I have a picture of such a thing here, but the question really is, how can we visualize it? And one way we can do it, if you look at this structure on the left here, you'll notice that we could think of x of E as a set of edges, and then we can think, well, there's this sort of function, this black function here, x of S, which is associating every edge with a source vertex, with a source, and then there's this function x of T, which is associating every edge with a target. So there's a couple of ways we can think of this. This idea on the right is probably easiest. So we can think of every edge then as going from some blue vertex to some other blue vertex according to the source and target functions. But then we also have this extra function x of D, which is associating every kind of vertex with something in this red set. So that's why it's called a vertex labeled graph, because this kind of green set and blue set are forming a graph. And then this kind of red function here, x of D, is associating every vertex in that graph with some member of capital X of V, either alpha or beta in this case. So that's why this is called a vertex labeled graph, because it's a kind of graph where the vertices are labeled with things from this set capital X of V. But then another way we can visualize this, if we have a look at x of V and x of L, we see we have a function x of D from one to the other. So we can visualize that as a bouquet. And then it is the loops of the bouquet, which are the members of x of L. And they're really what these kind of edges are going between. So we can think that there's this kind of graph with green edges, but the edges are not going between vertices, they're going between loops, the loops of this bouquet. So that's another way we can visualize this kind of thing. Okay, so here's another sort of related category. This one, C here. So in this case, where we have, objects E, V, and E, and arrows S and T from E to V, and an arrow D from E to V, well, we can think of this as the category of vertex parameterized graphs. Or if we like, we can think of it as the category of bouquet graphs with common sets of vertices. So again, we can just ask ourselves this simple question: what does a functor from C to set look like? And we can make pictures of it. I mean, obviously we can just picture the mappings. But the really interesting question is, how can we sort of visualize these things? Well, if we look at this thing on the left here, we can see we've got this kind of graph structure going on. We have this sort of graph. We have this sort of thing, xv, that we can think of as a edge set, and then we have these functions x of s and x of t associating edges with sources and target vertices. So yeah, we can visualize this as this kind of graph with blue vertices and green edges. And then what about this other information on the right? We have this function x of d from x of l to x of v. Well, one way we can think of this is there's just a function from x of l to the vertices of our graph, hence the name vertex parameterized graph. Or another way we can think of it is that there's a bouquet on the kind of vertices of our graph. So we have a graph, and then we also have a bouquet on the vertices. And it's up to us which of these types of visualizations we want to use. Okay, so just a couple more of these we want to have a look at. This is a very interesting case. So here we have these three objects, V, A1, and A2. And we also have these arrows. We have an arrow S2 from A2 to A1, and an arrow T2 from A2 to A1, and an arrow S1 from A1 to V, and an arrow T1 from A1 to V. And we also suppose that these are such that S1 after S2 equals S1 after T2, and T1 after S2 equals T1 after T2. So if we have this kind of setup, then it turns out we can think of the category set to the power of C as the kind of category of two-cell structures. So that is kind of things which are made out of these kind of two cells. Now, I'll show you an example of this very shortly. Of course, as usual, we can just think, well, the objects in this kind of category are just going to be functors from C to set. And so here's a kind of picture of what we can think of this kind of thing like. But the interesting thing really is this picture in orange on the right here. So this is really how we can visualize these kind of things. So of course, an actual, if we're being very so of course, if we're taking everything on face value, we just think, well, the functors from this are just so of course, if we're taking everything on face value, we think that the objects are set to the power of C are just going to be functors from C to set, and we can just sort of think about what they look like in this kind of arrow-based way. But what's really interesting is how we can sort of put more visual interpretations to this. So anyway, this object A2 is going to get sent to a set, this object A1 is going to get sent to a set, and this object V is going to get sent to a set. Now, we can think of these three sets. We can think of X of A2 as this kind of set of two arcs. And two arcs we can think of as kind of arrows between one arcs. So we can think of X of A1 as this set of one arcs. And then these kind of one arcs, we can think of those as just arrows pointing from one vertex to another. So we think of X of V as this set of vertices. And then X of S2 tells us which one arc a given two arc exudes from. X of T2 tells us which one arc a given two arc points to. So for example, alpha here points from A to B, because X of S2 of alpha equals A and X of T2 of alpha equals B. And then the kind of source and target of a one arc, which vertices they are, are given by x of s1 and x of t1 in a very similar way to what happens in graphs. Okay, so this gives us this kind of two-cell structure, but we do want these kind of equations to hold true. Okay, so finally, a very interesting case is this case of what I call triangulated spaces. So let's consider the case where C is this kind of category here. So we have objects T, E, and V, and we also have these three parallel arrows, delta 1, delta 2, and delta 2. And we also have these three parallel arrows, delta 0, delta 1, and delta 2 from T to E, and these two parallel arrows, S and T, from E to... And we also have these three parallel arrows, delta 0, delta 1, and delta 2 from T to E, as well as these two parallel arrows, S and T, from E to V. And we suppose that T after delta 0 equals S after delta 1, T after delta 1 equals S after delta 2, and T after delta 2 equals S after delta 0. So when we have this kind of setup, we can think of set to the power of C as the category of triangulated spaces. Now, this is just my own name for it. Well, I'll have more to say about how we can think of this in a wider context and connect with the other literature in a moment, but let's just think about what this actually means. So, the thing is that, obviously, as usual, the objects of set to the power of C in this case can be considered to be functors from this category C to set. Okay, so here's an object X, a functor from C to set. So what will such a thing look like? Well, basically, we're going to have these three sets, X of T, X of E, and X of V. And we can think of these as sets of triangles, directed edges, and vertices. Now, this function x of s, this associates every directed edge with a source. X of t associates every directed edge with a target vertex. Now, if we think about a particular triangle alpha, imagine that the edges are numbered. Okay, this is a bit rough, but it's a good idea to give you a sort of 1 minute introduction to the rather involved theory of simplicial sets. So imagine that the vertices are numbered, and so then if we have a sort of triangle, well, that would be a member of capital X of T, and then we can think of capital X of T as a sort of triple of vertices, 3 vertices, and then X of delta 0, we can think of that as the kind of edge of the triangle obtained by taking that triple of vertices and discarding the one with the lowest index. Similarly, we can think of X of delta 1 as getting that triangle and discarding the vertex with the sort of middle-sized index, and X of delta 2 we can think of as getting that triple and discarding the vertex with the highest index. So here's a sort of example. We can basically think of each member of X of capital T as a triangle. Now, when we sort of get one of these triangles, let's say alpha, and we do, let's say, X of delta 1 upon it, so here's alpha, and when we do X of delta 1 upon it, we look at the sort of middle side, so we look at the 3 vertices around the outside of alpha, there's 1, 2, and 3, we look at the one with the middle size, and then we look what's the edge opposite it, and that's C. So we think that delta 1 of alpha should be C. And also delta 0 of alpha is equal to B, because if we have a look at alpha, then its smallest vertex is 1, so, and the edge opposite that is B. So delta 1, so delta 0 of, so x of delta 0 of alpha is B, and so on. So hopefully this very brief introduction gives you enough information to be able to understand how x of delta 0, x of delta 1, and x of delta 2 work. And then these just allow us to associate these different sorts of triangles with directed edges, and then x of s maps a given directed edge to its source vertex, and x of t maps such a directed edge to its target vertex. And so basically all of these kind of maps and stuff allow us to describe how these kind of complexes of triangles stuck together are made, which is pretty interesting, especially, you know, when you think that all of these things I've just described are toposes. It's very nice to, you know, have all these different tools at hand to be able to study something so fundamental as spaces made out of triangles. Now, this is actually an example of a more general kind of concept called simplicial sets. And if you're interested in this, for example, if you want to generalize this kind of idea to tetrahedra or, you know, high dimensional simplexes and stuff made out of those kind of things glued together, I highly, highly recommend this document, An Elementary Illustrated Introduction to Simplicial Sets by Greg Friedman. You can find this on Google. It's like the first thing that comes up, at least for me, when I type in Introduction to Simplicial Sets. And yeah, it's very well written. Now, I should also say that if you're looking at literature on this kind of stuff, you're going to see this idea of pre-sheaves very, very, it's a very reoccurring kind of idea. And basically, a pre-sheaf is something of the form set to the power of C op, or some people would say it's the category of contravariant functors from C to set. So you can think of anything I've just described as a pre-sheaf if you sort of take the category of interest and reverse all the directions of the arrows. So, for example, this category, what I was calling this category of triangulated spaces, well, if we have this category C I've just drawn, let's say we take that, we reverse the directions of all the arrows, and we call the resulting category D. Well, then you could say, I'm interested in the category of pre-sheaves on D. And if you were, then you'd basically, this thing here would be the same thing as set to the power of C. Because what is a pre-sheaf on D? Well, it's just a contravariant functor from D to set. Or if you like, it's a covariant functor from D op to set. What's D op? Well, if D is the opposite category to C, then D op is C, and so it would be an object of set to the power of C. So basically, by reversing directions of arrows, you can make this connection with pre-sheaves. So, you know, a lot of the literature about these interesting kind of categories of functors from C to set are in terms of pre-sheaves. For example, there's a brilliant book, Generic Figures and Their Gluings, that talks about so many of the things I'm going to go into today in even more detail. But they pitch everything in terms of pre-sheaves, which I actually think makes things look a bit more complicated at the beginning, and it's not nice to have these kind of initial barriers. But anyway, it's still a wonderful book.